All right, our next speaker is Dr. BJ Fulton, who is a senior application developer at NExScI. BJ has been involved in many Sagan workshops, so we have a lot to thank him for, including the Radvel package, which I'm sure many of you use, and our research. So the topic of this talk is, what is a sub-Neptune?
All right, thanks, Courtney. Thank you. It's on, right? Yeah. All right, yeah, thanks, Courtney, and to the organizers for inviting me to give a talk on this exciting and very broad question about what is a sub-Neptune. So let's get into it. So let's start with some motivation. So Kepler showed us that planets smaller than that of Neptune, between the sizes of Earth and Neptune, are extremely common. They're about an order of magnitude more common than their larger counterparts, the giant planets that Brendan was just talking about. But we have no example in our own solar system, obviously. So it's hard to conceptualize and visualize what these planets are. They span a range of sizes and masses and likely compositions, and we're still trying to really understand what defines this class. Is it simply a size effect? Is it mass, atmosphere, formation history? We don't really know yet, but it is clear that understanding them is key to understanding how planetary systems form and evolve. One of the biggest clues about what makes a sub-Neptune and differentiates it from other classes of planets is the planet radius distribution of small planets. In 2017, we discovered that the radius distribution for these small planets is not smooth. Planets smaller than Neptune don't come in random sizes. They tend to prefer to come in two, either about 1.2 times the size of Earth or about 2.4 times the size of Earth. And we see a significant dearth of planets between them. Just simply based on density arguments alone, we can pretty confidently say that planets smaller than this gap in the radius distribution tend to be dominated by rocky compositions. And planets larger than this gap definitely have to have some sort of volatile atmosphere on top of a core. So this radius gap does seem to separate two physically distinct populations. And you can see this again if you actually go and look at densities. So here I'm plotting density on the y-axis and then still radius on the x-axis, along with some iso composition lines. So you can see a planet that's pure iron composition would lie someplace along that line in the upper left. You can see that the population of these smaller planets on the left side of the planet radius gap tend to be consistent with some mixture of Earth-like composition, so a mixture of rock and iron. Once you get to the right side of this gap, the slightly larger planets, you have to add some hydrogen, helium, or some sort of volatiles on top of that in order to explain their bulk density and their mass and radius. So let's start with a working definition of these. I'm just going to go ahead and say right now that these are planets with radii between 1.7 and 4 Earth radii, so smaller than Neptune, but larger than the center of that gap, at least for short periods. Their masses, for the ones we've measured, typically span between about 3 and 20 Earth masses. And like I've mentioned a couple times, their bulk density indicates that they're less dense than pure rock or a mixture of rock and iron. They need to have some sort of volatiles. Now that might mean a big gas envelope on top of a relatively dense core. It could mean water worlds dominated by a lot of water and a thin atmosphere on top, or some combination of both. And it really leaves us with a pretty broad range of possible internal structures that can fit this mold. So I'm going to go through some plausible explanations for what causes that gap in the planet radius distribution, and I think that'll help us understand what these things are made of a little bit better. So first of all, from a very simple perspective, let's start with a cartoon example of a planet here. So this is going to be let's see, two Earth mass planet I've created here with 30% iron and 70% silicates, similar to an Earth-like composition. Such a planet with that mass is going to end up right here on the planet radius diagram, about 1.2 times the radius of Earth. Now, if you add just a little bit of hydrogen helium, just 0.2% by mass hydrogen helium envelope on top of that same rocky core, that would put you right in the middle of this gap. But a tiny bit more hydrogen helium, 2% now, and now you're solidly in the peak of the sub-Neptunes, or the slightly larger planets in the regime of small planets. If you continue to add more gaseous or volatile envelope on top of that rocky core, you quickly increase your radius. And so now if you get up to 10%, you're going to be around the size of Neptune at about 4 Earth radii. And the key thing to understand here is that there's just a very small phase space for planets to exist within the gap. Regardless of formation mechanisms and their history, just a randomly distributed system of planets with varying hydrogen helium envelopes, it's going to be relatively rare to find one in this gap because they have to have somewhere between 0.3 and 1% hydrogen helium by mass, or volatiles by mass, to be in that gap in the first place. You could fill in that gap with a wide distribution of the core sizes. You could make it work, but the argument is that the planets grow very rapidly as you add just a little bit of volatiles. So maybe one of the most widely adopted theories that explains the gap is photo-evaporation. And this was a great example that Brendan was mentioning of a theory coming out with prediction of what the planet population should look like. And then we went and observed it and saw exactly what was predicted by Owen and Wu 2014, Lopez and Fortney 2013, and others around that time. So what I'm plotting here on the right is a mass loss timescale as a function of envelope mass fraction. So what happens here is that in the first 100 million years of a star's life, or so, depending on the stellar type, there's a lot of extreme ultraviolet photons being emitted by that star, and that can quickly erode atmospheres. So if you're on the right side of these curves on this plot, that means you started with a very large envelope mass fraction. It gives you a very large radius, a large surface area to absorb those XUV photons, and that quickly erodes away that big puffy atmosphere. You end up being somewhere near the middle of this plot where it peaks, and once you get above that horizontal dotted line there, that's the 100 million year mark where most solar type stars stop emitting so many extreme ultraviolet photons. And so if you started on the right, you're going to get evaporated away up to the point of 100 million years. You'll end up somewhere around that peak with a few percent by mass hydrogen helium envelope. But if you started to the left of that peak, if you started with a small envelope mass fraction, over the course of that 100 million years, even though you're smaller and absorbing less, it's going to be easy to evaporate away all of that atmosphere, and you're going to end up with just a bare rocky core. That tends to sort of herd these planets into these two groups that you see in the planet radius diagram. All right, to understand this a little bit better, we'll go through another cartoon example here of how this works. So here's a planet that did start on the right side of this mass loss timescale plot with a large 20% hydrogen helium envelope on top of a 3 Earth mass core. Like I said, that big puffy atmosphere is going to absorb a lot of the flux from the star. And during that first 100 million years, it's going to get evaporated away. Now, at this point, you've crossed that horizontal dotted line there, and you've ended up at 3% hydrogen helium by mass. And that puts you at about 2.4 times the size of Earth, right in the peak of of the slightly larger planets, or the sub-Neptunes. if you were to start right in the middle of that gap, say with a planet that has 0.3% hydrogen helium by mass, irradiate with a very similar star for 100 million years, you can see now you're on the left side of that peak. And over the course of that 100 million years, it's going to get evaporated away completely down to just the bare rocky core. And at that mass, that composition, you're going to end up about 1.2, 1.3 times the size of Earth. Another way to look at this is to simulate a population of planets. Hopefully I can get the movie to play here. Yeah. So if you splatter a bunch of simulations of planets with a variety of core masses and atmospheric envelope mass fractions, you can watch them evolve over time if you expose them to simulated extreme ultraviolet flux. So here we're following a particular planet from this simulation here. It starts very large with a large envelope mass fraction, and that puts it up at a radius of about 7 times the size of Earth. As you irradiate that, that large puffy atmosphere absorbs a lot of that at first and quickly evaporates it away down to a few percent by mass, hydrogen helium. And you end up, stalling in this regime of 2 to 3 times the size of Earth for a while. You see, it evaporates very fast at first, then it slows down significantly between 2 to 3 times the size of Earth. But then once it gets past a certain critical point and you get a small atmosphere, you can see it quickly drops right across that gap. And that's why we don't see so many planets within that planet radius gap. It's simply because the planets that are forming or have formed spend very little time there. So when you see a snapshot of a bunch of systems, it's very unlikely that you're going to see any in this gap. There are some there, it's not completely empty, but they're much less common to observe them there than elsewhere. I did mention that this is one of those ideas that was very well predicted by theory, and you can see here on the bottom is a plot of planet size on the y-axis versus insolation flux on the x-axis here. On the bottom is the prediction from models of photo-evaporation being the dominant sort of driver of this population, and on the top was the observations that we saw from Kepler, which match very well. The location of the gap in terms of planet radii also tells us something important about the compositions of those cores, the densities of the cores themselves, and that has some implications perhaps for their formation locations as well. So on the right here, I'm showing the planet radius distribution in that light gray with a few simulations from if you assume that cores are all iron versus all silicate and all water in the various colors there. The amount of hydrogen helium that it holds onto, that 3%, is determined by the surface gravity at the top of those cores, which is determined by the densities of those cores. So if you have a solid iron core, or if there are a population of these solid iron cores, that would push this radius gap to much smaller radii. If you have water, it would push it towards larger radii. And so what we end up observing is that it falls between sort of the pure iron and the pure silicate regime, somewhere near Earth-like compositions. So photo-evaporation is definitely a popular way to interpret and explain the planet radius gap, but it's certainly not the only one. There's been ideas that an influx of pebbles during late stages formation of these planets can sufficiently heat and drive off the atmosphere as well. You could do the same thing with giant impacts instead of a bunch of small impacts as well. You could also go the other direction. You could evaporate it away completely or start with very little atmosphere and then outgas a few percent by mass of volatiles from volcanism at very late stages and still end up with a similar radius distribution. Or you can simply have primordial heat left over in the cores of these planets. that then leaks into the atmosphere and drives atmospheric escape as well. I'll say probably the photo-evaporation and the core heating models tend to reproduce the observations the best. And the main way to distinguish between these ideas is the slope of the radius valley. So how that radius goes to smaller radii as you get to longer orbital periods, or especially lower insolation flux. Now, these all seem like quite different formation mechanisms, but they do have common threads. Basically, the idea behind all of these is that you assemble planets into rocky cores early on. You add gas at some point, either during that formation time, shortly after, or even late stages. And then you add heat to that atmosphere, and that drives the atmospheric escape. So fundamentally, the radius gap marks this dividing line where on one side we have planets that held on to a little bit of their gas, or maybe formed with their gas. And on the other side, they didn't. They've lost all of their atmospheres and they end up just as bare rocky cores. And so those I'm gonna call super Earths and continue to talk about these sub-Neptunes or mini Neptunes that retain some of their gas and end up on the right side of that planet radius gap. Now, these were all based on statistical arguments and observations of the population. But what we really would like to see is what these planets really look like and observe them one at a time and start to get a good sample of what these things look like. So GJ1214b is maybe one of the most famous sub-Neptune planets. It's about 6.5 Earth masses and 2.7 Earth radii. So it's right in the middle of that sub-Neptune peak in the radius distribution. And probably what makes it so famous and iconic is how hard it has been to characterize. There's a famous study by Laura Kreiberg in 2014 where she gathered an obscene amount of HST time to observe the transmission spectrum of this star. So she was looking for, absorption features from the light that pass through the very thin annulus of its atmosphere to see what might be the composition. And after this huge amount of HST time, it looked exactly the same no matter what wavelength you look at. It looked essentially like a solid, opaque body with nothing interesting going on at all. Now, we know that from the mass and radius alone, it can't just be a solid rocky surface. So the idea at the time was that it's obscured with haze and other opaque clouds that we can't see below. She also observed many other systems as part of this program, and many other people did with HST. And basically, every sub-Neptune that we observed with HST using transmission spectroscopy ended up having a very flat, uninteresting spectrum. So I have given this talk or similar to this over the years many times, talked about this radius gap. But I think this is the first time that I'm talking about this since we've started getting data from JWST. So now this is a very exciting time because we are actually able to start measuring the atmospheric compositions of these sub-Neptune planets with JWST. So of course, one of the first to be revisited was GJ1214. But this time, instead of trying to only look for the effect of the light coming through that very thin annulus of the atmosphere, this team instead looked for the thermal emission from the planet. And so now you're getting all of the signal from the infrared light that's being emitted from lower down in the atmosphere and then being absorbed from the upper layers of the atmosphere. And you can see the absorption lines in the spectrum that way, similar to how we measure the composition of stars. So what they found is that the envelope mass fraction needs to be relatively high, around 8% by mass. and they found what I would call sort of tentative detection of water absorption in the spectrum as well. So in the black little diamonds there are the observations, and the lines are models. And you can see from 6 to 8 microns, there's pretty strong absorption. It's almost black in those wavelengths. This is, I think, a plot from the night side. They did this for the day side as well, and also saw similar absorption features. So if you combine the two, it's more significant than it looks in this one plot. But yeah, they do claim detection of water. Um, it it's not enough water to explain it, the atmosphere being fully water. Basically, it has to be a combination of high mean molecular weight atmosphere. So it's a rich metal rich atmosphere. That's probably what producing the haze. Um, and uh, and then there's water mixed in as well. So, oh, and the other argument that we can now really be fairly confident that we're seeing the tops of clouds instead of the surface of a rock is that the bond albedo is very high at about 0.5. This is 3 or 4 times higher than the typical terrestrial planets that we see in our solar system, and much more similar to Jupiter, where, of course, we're observing the tops of the clouds that are very reflective. So it's highly reflective, which is another indication we're seeing the tops of clouds. Um, and TUI 421 is another interesting hot sub-Neptune that has been observed recently by JWST. And this one's very hot. So it's much hotter than the previous example. It's much more heavily irradiated. And this is one of the clearest detections of a clear sky, essentially. This one shows a lot of water features in the atmosphere, as well as a little bit of carbon monoxide and sulfur dioxide. But the interpretation here is that it's very rich in hydrogen, and this is a good example of one of those planets that is likely a rocky core with a large hydrogen helium envelope on top of that. Um, and then an exciting discovery from of K2-18b here, yet another sub-Neptune, a radius of about 2.6 times the radius of Earth and 8.6. All three of these are right around that same mass and radius regime, but they have very different irradiation environments, at least at the current stage. This one is actually in the habitable zone of its host star, but it's orbiting an M star. And M stars don't really follow that rule that the first 100 million years they emit a lot of the extreme ultraviolet flux. They continue to release UV flux throughout their lives, especially through large flares. So this may look a little bit different than the rest of the population, or these planets orbiting the M stars might not be quite as similar to the ones that I've showed that contributed to the radius gap from Kepler that are mostly solar type stars, but it's still an interesting comparison. And it is a sub-Neptune planet here that we can observe pretty well here. This one also seems to have a somewhat hydrogen-dominated atmosphere, but we also detect methane and carbon dioxide at pretty high significance. So there's lots of hydrocarbons here. They also have a somewhat tentative detection of dimethyl sulfide, which is, at least on Earth, produced by biological sources, but it can be produced by non-biological sources as well. And it's also lacking in nitrogen or ammonia, sorry, which is potentially evidence that it has somewhat of a liquid water surface as well. So this just adds another dimension to the diversity of sub-Neptunes that we're seeing. I've only showed 3. I think Joanne's going to go into a lot more detail on the atmospheric results from JWST, and we'll see some more of these. But it's just 3 examples that show how diverse this planetary population really is. So let's go back to revisit our definition here. I think the radius is still a pretty good way to define these planets, at least for now. We still don't have a much better way to do it until we start getting a large sample of these atmospheres and we can start understanding the atmospheric demographics of these planets. I mentioned it has to have some sort of volatile rich atmosphere. but it doesn't necessarily have to be hydrogen, helium, or water. It can be heavier elements as well. They are certainly structurally distinct from rocky surface Earths. We can see that in a lot of ways, primarily in the bulk compositions and densities. And they're almost certainly shaped by their formation location and their evolution as they form and through the first 100 million years or a bit longer of the star's existence. We still don't know a lot about these, including what fraction are water rich versus, or have even heavier elements versus what look much more like miniature gas giants that are hydrogen helium dominated. Like I said, I think we need a good large sample of atmospheric characterizations to start to understand that well. We'd like to understand how often or if these things can host liquid water oceans, the ones that are in the habitable zones. What do those ones look like? And we'd like to understand the balance between nature versus nurture. How much of their final locations in that radius diagram, their final characteristics is determined by the initial conditions of their formation versus the first, few 100 million years of their existence. But the biggest question, of course, to me anyways, is why does our solar system lack one? And I think there's a lot of dynamical arguments and studies that look at the planets remaining in our solar system to try to understand what could have happened that prevented our solar system from ever having one or ejected one of these. Where do these go in our own solar system? And so in summary, I've shown that these things are very common and the radius gap is a good way to distinguish between these two populations of planets, those that could be fully rocky and those that have to have some volatiles that are these sub-Neptunes. And JWST is just beginning to peel back the haze and measure the atmospheric compositions of these things directly to really better understand what they're made of. And with that, I'll take any questions. Thanks.
Yeah. Come on forward if you have questions. And if you're online, please put your questions in Slack. We have a couple discussions in Slack as well. There's a question from William Forrest about the spectrum of GJ1214b, specifically asking whether there is carbon dioxide causing a huge dip at 15 microns.
I believe they did detect carbon dioxide, but I can't remember for sure. I might encourage you to ask that same question to Joanna next, who will be talking exclusively about the atmosphere. Yeah.
Good plan. All right.
Hi, hello. Thank you for the talk. You mentioned some of these like potential Hycean water worlds versus sub-Neptunes. Do you expect them to have fundamentally different formation mechanisms, and would that affect the atmospheric mass laws that you've been running?
Yeah, planets, so most of them that we observed from the Kepler sample are very close in, and they're well within the water ice line. So it's difficult to have a large water fraction on those planets if they formed there. So yes, planets that have significant amounts of water probably indicate that they would have formed farther out in the disk and then migrated in. And that's another thing that comes from this plot here on the right. That shows that most of these cores are a mixture of iron and silicates. It probably indicates that these things didn't migrate from well out in the disk, at least not after the first 100 million years, because they don't have a huge water fraction.
Cool, fantastic. Thank you.
One more question.
Hey, great talk. I really liked it. I was just wondering how photo-evaporation changes with different stellar type, stellar age.
Yeah. So the big difference is once you get down to the M dwarfs, like I said, it continues periodically throughout its life. So you don't have the sustained XUV irradiation all throughout the M dwarf's life, but you have flares that happen and can have a huge impact on blowing off atmospheres. So you could have one flare event that drives away a huge atmospheric escape. So I think it becomes much less clean to understand the population of these planets around M dwarfs because you don't know, how big of a flare it's been through yet.
Mm-hmm.
Yeah.
Thank you.
Let's thank Dr. Fulton again.